In this video, we'll be looking at heat transfer in convection. So now when you talk about heat transfer in convection, you're referring to the heat transfer from a solid surface to a fluid or to the atmosphere. So anytime we have a solid surface exchanging heat to the atmosphere or exchanging heat with a fluid, then we see that convection is the form of heat transfer which is actually taking place. So the fluid, I mean air or liquid, or let's say gases or liquid. So now we have a question which says that a 2-meter long, 0.3 centimeter diameter electrical wire. So we have a wire which has a diameter of 0.3 centimeters and then a length of 2 meters across a room at 15 degrees Celsius. So now we have our room, right? It extends across the room. So if you are treating this as our room, and then the room has a temperature of 15 degrees Celsius, heat 90 watts was in the wire as a result of resistance heating, and the surface temperature of the wire is measured to be 152 degrees Celsius. So now the wire has a surface temperature of 152 degrees Celsius. That means at each point, the temperature is 152 degrees Celsius, even at this point also. The question asks is that disregarding any heat transfer by radiation, determine the convection heat transfer coefficient for heat transfer between the outer surface of the wire and the air in the room. So now the wire extends across the room, yes, and then the wire has a temperature of 152 degrees Celsius, and then the room has a temperature of 15 degrees Celsius. So now when we see the room has a temperature of 15 degrees Celsius, actually we are saying that the air in the room has a temperature of 15 degrees Celsius. And then since the wire extends across the room, the part of the wire that has the temperature of 152 degrees Celsius will exchange heat with the room because it has a higher temperature than the room's temperature. And we know that heat always transfers from the hotter body to the colder body. So now, but when we are looking at this question as a whole heat transfer question on its own, then heat of radiation is also going to take place. Why? Because part of the wire is also going to release heat to the atmosphere, which is the part of the wire which is not in the room. Now, the whole of this part and the whole of this part is also going to transfer heat into the atmosphere. But now the point is that we are assuming that the entire wire passes through the room, right? So this is actually what's happening. So the entire wire passes through the room. So now we have all the wire in the room. This is what the question is actually asking us to find. We have all the wire in the room, and then it has a length of 2 meters and then a diameter of 0.3 centimeters. Because if only this part, we are assuming only this part to be in the room, then we are supposed to be given the length of the part which is only in the room. But now, because you've been given the entire length of the wire, it means that all the entire length of the wire was actually passing through the room. So now, the moment we find out that the heat transfer problem we are having here now is convection, then we can only resort to the Newton's law of cooling. Newton's law of cooling. The Fourier transform, the Fourier transfer equation is for heat transfer in conduction, but the Newton's law of cooling is for heat transfer in convection. Then the Newton's law of cooling states that our Q is equal to HA multiplying Ts minus T infinite. So now our H represents our coefficient of heat transfer, and then our A represents our area, which we are dealing with, area of heat transfer, and then our Ts is the temperature of the surface which is losing the heat, and then our T infinite refers to the temperature of the fluid. Yes. So now here we've been given our Q to be 90 watts. Now we have to find our area, and our area is we're looking at the area of the surface. So now this is a cylindrical wire. and then the surface has 152 degrees Celsius. That means you have to find the area of the surface, AS. Now the area of the surface is going to give us 2 pi RL. So now the curved surface area is actually 2 pi R. And then because it has a length, it's going to be 2 pi RL. Or you can say pi DL. We've been given a diameter to be 0.3 centimeters. And because we have our length to be in meters, so let's convert our centimeters into meters. We are going to have 0.3 times 10 to the power negative 2 meters. So our area then becomes pi times RD, 0.3 times 10 to the power negative 2 times our L, which is 2 meters. And then doing that, we are going to get our area to be 0.0188 meter squared. So now this becomes our area. Now the question asks us to find the heat transfer coefficient, which is our H. So now our H is equal to Q over AS T minus T infinite. Now our T infinite is the temperature of the fluid, which is the temperature of the air in the room, 15 degrees Celsius. And our Ts becomes 152 degrees Celsius. So now our H becomes 90 all over 0.0188 multiplying 152 minus 15. And then doing this, we are going to get 90 over 1 over 0.0188 multiplying 152 minus 15. We're going to get 34.94. So now our H is 34.94. Now when we want the units, we know that our Q is in watt, so write watt. Okay, our area is in meter squared, and then our temperature is in Celsius or degrees Celsius or Kelvin. I've already said that if we are looking for a change in temperature, then our change in degrees Celsius will always be equal to our change in Kelvin. So we can say watt per meter squared Kelvin or 34.94 watts per meter squared degree Celsius. It's still the same thing. This is the end of the video.